So today we're picking up with the fundamental theorem of algebra. Did anybody else see this before you find out? Okay, so fundamental theorem of algebra is basically talking about, do all polynomial functions, does every polynomial function have a zero, which means can we at least find one number which will be a factor, or basically you can think about it as a solution, right, to our polynomial function. So this answer, this question was answered, they're saying, in the affirmative by Carl Gauss or Gauss, depending on how you pronounce it, where he proved that back in 1799. So we're saying as long as you have a polynomial function with a positive degree, you can find at least one zero, but they're saying that zero can be in the set of complex numbers. So they're saying as long as you have a polynomial function with a positive degree, it will have at least one zero, and that zero will be in the set of complex numbers. So when we're talking about complex numbers, we're not talking about just real numbers anymore, right? When we say complex numbers, we're saying it can be in the real set, but it can also be in the imaginary set, right? So they're saying if you expand your set to include imaginary numbers, then yes, we can at least find one zero to our polynomial function. Now again, we know that the number of zeros for a polynomial function are based on the degree of the polynomial function itself. So if it's a degree n function, then that means at most I can have n zeros for my polynomial. So again, if it's a third degree polynomial, at most I can have 3 zeros. Second degree polynomial, I can have 2 zeros at the most. So that's kind of what this little theorem talks about. Okay, so with the quadratic function, we can use basically the quadratic formula and find what these zeros are going to be. So that's a really straightforward way. Now, of course, we can use factoring. We looked at other methods where we can use completing the square and the square root property. This was back in chapter 1. So we saw all of those different methods to solve a quadratic equation, basically, or a quadratic function. But once we get into higher degree polynomials, it's not quite that straightforward anymore. So a lot of these methods that we will be looking at will help us narrow down the possibilities of what numbers can be our zeros for the polynomial, but they're not going to give us the exact answer like the quadratic formula does. So a lot of these theorems, as I mentioned, are going to help us narrow them down, but they won't help us find the exact answer like it does with the quadratic function. So the rational zero theorem actually helps us list what are all the possible options that I can have for my zero of my polynomial. So the way this works is, let's say this is our polynomial function here, highest degree n. So a sub n basically means the coefficient that goes with the highest degree of the polynomial term. And then of course we start going down by 1 in our degree till we get to 0, right? So a sub 0 will be our constant term. So when we're talking about the rational zero theorem, we actually look at P over Q factors. P over Q is calculated by looking at all the factors of the constant term, that defines the P, and looking at all the factors of our leading coefficient, which defines the Q. So the way we list all these possible rational zeros is take the factors of the constant term, divide them by the factors of the leading coefficient. So for rational zero theorem, the intermittent terms, the ones in the middle, are not going to make a difference at all. You just need the leading term, you need the constant term, you take the factors of those terms, divide the constant factors by the factors of the leading coefficient. So the way this guy will work is, just as an example, let's say this is our expression here, 6x squared minus x minus 35. Right, so I'm only interested in the constant term, and I'm only interested in the leading term. So if we look at all the factors of 35 and 6 in this case, so let's go ahead and write those down. So our expression is 6x squared minus x minus 35. So all the factors of the number 35. So for P, it's going to be the term 35, which is the constant term. And what are factors of 35? 1 and 35. What else? 5 and 7, yeah. So all four of these numbers would be considered the factors of 35. When I multiply them, I get 35. Q comes from your leading term, which in our case is 6 for this example. So factors of 6 will be 1, 2, 3, 4. Yeah, 1 and 6, and then 2 times 3. So 1, 2, 3, and 6. Now the idea is when I'm looking at all the possible options, so what are all the different possible rational zeros? I'm going to take each one of my values for P and divide it by each of the values for Q. So that would be 1 divided by 1. So that's the first two from here. And then 5 divided by 1, 7 divided by 1, and so on and so forth. So 5 divided by 1, 7 divided by 1, 35 divided by 1. And you keep repeating this process. So we have divided by each of these factors from Q. So that would mean we're now looking at 1 divided by 2, 5 divided by 2, 7 divided by 2, and 35 divided by 2, and we would keep continuing this process. The other thing we also have to take into consideration when we're doing this is concept of our numbers being either positive or negative. So you can see just by including the positive and negative, we double the number of possible options we will have because we still have 2 more of these numbers to divide by, right? And I'm not going to list all of them because this is a pretty long list in here. But out of all these possible rational zeros that I can have, you will notice the only 2 that work are 5/2 and negative 7/3 out of all those possibilities. So that's what the rational zero theorem basically does. It gives you all the different options that could work, but they don't tell us which one is actually going to work. So that's why we need kind of to bring all of these bunch of different theorems together to be able to find what zeros we will have. Now this is again a second degree polynomial. So as you can see, you can basically just factor 6x squared minus x minus 35, set each of our factors equal to 0, and we can find our zeros that way. So 2x minus 5, set that equal to 0, we get x equals 5/2. 3x plus 7, set that equal to 0, we get negative 7/3. So those are the 2 factors for our polynomial here. Now again, you can see 5 and negative 7 actually came from the factors of negative 35, and 2 and 3 came from the factors of 6. So that's how this rational zero kind of works out in this case. And then it's kind of basically telling you that same thing here, that the theorem does not identify exactly which ones are the zeros. It only gives you the possibilities for your rational zeros. So let's see what happens here in number 5. They're asking us to find all the possible rational zeros. So we are given h of x equals 2x to the third plus x squared minus 4x minus 3. So again, we're only interested in the constant term and the leading coefficient. We don't really use any of the terms in the middle here again. So let's look at factors of, and since that's a -3, let's go ahead and include the sign with r. It really doesn't matter because we end up doing plus or minus on our possible rational zeros, but you can bring in the negative sign here. So factors of 3 will be what? 1 and 3, right? So when I bring that negative sign in there, I can have factors as 1 and negative 3, or I can have factors as negative 1 and 3, just depending on what combination we use. For Q, that's going to be the leading coefficient, which is a positive 2. So factors of 2 will be 1 and 2, yeah, prime numbers, so you don't have too many choices there. So what will be our possible rational zeros? So again, remember it's always in the order of P over Q. So that's going to be 1 divided by 1, 3 divided by 1. I'm actually going to save us some time and just use 1 and 3 as my factors for 3 here, and I'll tell you here in a minute why I'm doing that. So I've got 1 divided by 1, 3 divided by 1, and then same thing, we take 1 divided by 2 and 3 divided by 2. If we only think of factors of 3 as being 1 and 3, and then we always need to think of the possibilities of these guys being positive and negative, so that automatically takes care of when one was negative 3 and negative 1. It already includes that in our calculation. So honestly, for our factors, you don't need to think about bringing the sign in when you're doing the factors here, because when we do plus and minus, we already take that negative into consideration. So for this polynomial here, we've got basically 8 different options, right? Now the idea is one of these could be a factor, 2 of these could be a factor. This is a 3rd degree polynomial, so 3 of these could be a factor, but we don't know. We don't know how many of these are going to be factors, and we definitely don't know which ones. So the rational zero theorem is just giving us what possibilities do we have. Now, if we go back to our handout, they're telling us our goal is to find the zeros for the polynomial function, which might be a rational number, it can be an irrational number, or our zero can also be an imaginary number, as we saw with that fundamental theorem that Carl Gauss talked about. So they're saying we can determine this by simply evaluating our polynomial function at the, basically by using every number in the list, which would mean you take each number, put it in your function, and see which one gives you a 0. Or they're saying you can look at the graph, but we know graphs cannot be concrete solutions. Or they're saying use synthetic division. So either plug in the number into your function and see, do I get 0 as the answer? Use synthetic division to see which one gives me a 0 remainder, and I would use graphing as my very last option. So this is actually the same example from number 5, 2x to the 3rd plus x squared minus 4x minus 3. So since we already have our list of possible options, in number 6, they're saying find all the zeros. So when you're finding all the zeros, you're basically testing to see out of these 8 options, which ones are going to work. Now, of course, the ones that are being divided by 1, you know, these guys are going to be plus or minus 1, plus or minus 3. And then these ones, of course, will be our fractions. So we're checking out of these 8 options to see which one of them is actually going to be a 0. We're not going to check all 8 of them. It does take a long time to do that. I have, however, given you enough space on both sides if you wanted to check, but I think I'm going to check just a couple of these. So let's start with positive 1. So I want to see if positive 1 from one of our options is going to give us a 0 remainder or not. What numbers do I put inside my synthetic division from my polynomial in here? 2, 1,
-4,
-4,
-3.
-3. Alrighty, very good. So again, we know the first number just comes down as it is. And then you start multiplying. So we do 2 times 1, which is 2. Then we add 2 plus 1 is 3. 3 times 1 again is going to be 3. -4 plus 3 gives us -1. And again, when we multiply this -1 with 1, and we did not get a 0 remainder now, did we? So this is our remainder. It is non-zero, which means 1 does not work for us. All right, we've tried 1. Now we go back and try for -1 from our list. So -1 will give us, again, 2, 1, -4, -3 from our polynomial. Bring the first term down as it is. And what kind of remainder do we get with this guy?
0.
We do? Yep. Okay. So let's see, that guy is -2. -2 plus 1 is -1. -1 times -1 becomes +1, which is -3. 2 negatives makes it a positive. Very nice. We in fact get a 0 remainder. So that means this guy is going to work. All right. +3 and -3 do not work from what I remember. So we're not going to waste our time checking those. Okay, the 1/2s don't work out either. So let's check. Let's check with 3/2. Okay. So we've got 2, 1, -4, and -3. So positive and -3 don't work. Positive and -1/2 doesn't work. Of course, we saw 1 doesn't work. So far, the only answer that does work is -1. This is a 3rd degree polynomial. So remember, at most, it should have 3 roots. What do we get with positive 3/2? So when you're multiplying 3/2 with 2, what are you going to get? We're multiplying 3/2 with 2. It should be 3, yeah. Because these guys will cancel out, giving us a 3. 3 plus 1 is 4. 4 multiplied into 3/2? 6. Yeah, very good. This 2 goes into 4 2 times. 2 times 3 is 6. 6 minus 4 gives us 2. What is 2 multiplied with 3/2 again? 3. 3, yeah. And -3 plus 3 will give us a 0 remainder again. So that tells us this is going to be one of our other roots, right? So we've got -1 and we've got 3/2. So the idea your textbook has is you should be checking all 8 of these options to see which of them is going to work. That's a lot of work for us to do. So this is what I recommend. Once you hit your first zero remainder, right? So I wouldn't have gone back and checked for the 3/2. Once I got my -1 at my 0, I would actually go back and work with the quotient now instead of going back to the other option. So what is this quotient going to be?
2x squared
2x squared
minus x
minus x
minus 3.
minus 3, and I would take this guy, set it equal to 0, and try to solve this. Solving a second degree polynomial is still pretty easy. Can I factor this? Actually, I think we should be able to. 2x squared minus x minus 3, so of course the 2x squared, we can break it down into 2x and x. Since I have a negative on my constant term, that means I will have opposite signs in this parentheses. So factors of 3 for this guy will be 3 and 1, right? Now we just got to decide, where do I put the 3, where do I put the 1? Where do I want to put the 3? With the 2x or the x?
The 2x.
You do want to put it with the 2x. And the reason we want to put it with the 2x is because we've already done the work and we know 3/2 comes out to be one of our roots, right? So you know that's going to come from this factor. That also means I need to have negative for the 3 and positive for the 1. When I multiply, -3 times 1 gives me -3. When I add, that means I will be multiplying -3x and then positive 2x. So -3x positive 2x will give me my -x. So factor this. If factoring is something that doesn't seem obvious to you, you can also use the quadratic formula here. Take each factor, set it equal to 0. This guy gives me x equals -1 as one of our zeros. And this guy gives me positive 3/2. And remember, this is in addition to the -1 that we already found. Because this quotient is coming after we got -1 as our 0, right? So these two factors that I'm getting are in addition to the -1 that I already have. So this is how it's working. I have 3/2, and then I have -1 and -1, which is getting repeated. So those are my 3 roots that I'm coming from. So your roots for this example are going to be -1 and 3/2. You of course don't need to write the -1 twice, but we know that it has an occurrence of 2 times. Even if you would have checked for -3/2, it wouldn't have worked. So the only numbers that work out of that whole list of possible options that we got in number 5 is only going to be -1 from here, and then positive 3/2 from here. Of course, these two are not going to work in the middle, or actually 4 options from that one. So here's what I'm suggesting for you guys. Once they're asking you to find all the possible zeros, start with your rational zero theorem. These were only 8 options, which is still pretty manageable. So start by checking with the numbers, and hopefully in the first couple ones, you should be able to find where your 0 remainder is. By default, I always start with the 1s. So I'm like, hey, if one of those 1s works out, my life is going to be really easy, right? It goes pretty fast to check with 1 or -1. So as soon as one of them works, you get a 0 remainder. You have found one of your zeros. To find the others, just take the quotient and break it down. If it's a second degree polynomial, you can try factoring or the quadratic function to solve it, and you should get additional zeros from that. So you wouldn't have to go back and check any more of your list. Okay, so that's what I'm suggesting here. All right, guys, questions on number 6. So number 7 here is again same thing. They're asking us to find all real and imaginary zeros for this polynomial here. This is again a third degree polynomial. So let's start by finding our rational zeros first. So this one is f of x equals 3x to the third power minus 2x squared plus 12x minus 8. So we will start by finding factors of p, which is our constant term, the number 8, and I'm not really going to worry about the negative sign this time. So factors of 8.
1, 2, 4.
Yeah, 1, 2, 4, and 8. And our q term comes from the leading coefficient, so that would be the number 3. And factors of 3 would be just 1 and 3, right? So what will be our possible rational zeros? Okay, so I will take 1 divided by 1, 2 divided by 1. Remember, again, these are always in the form of p over q. 4 divided by 1, 8 divided by 1, and then repeat by dividing by 3. So 1 divided by 3, 2 divided by 3, 4 divided by 3, 8 divided by 3. And then we include positive and negative on all of them. If you just clean this up, we should have positive and negative 1, positive and negative 2, positive negative 4, positive negative 8, positive negative 1/3, positive negative 2/3, positive negative 4/3, and 8/3. So how many options are those? A lot. Specifically?
16.
16, yeah, because we had 8 of these, and then the positive and negative doubles them and makes them into 16. So for your insanity and mine, we're not checking all 16 of those. Trust me, we don't have the time. So I will tell you which one works. And as the case would be, out of 16, one single one of these works. 15 of them don't work. So you can see the evil process that this is involving, because this can be very time consuming, but even that's what happens when you get to higher degree polynomials. There is really no straightforward way. It becomes pretty tedious. So a lot of times you will see in algebra courses, we just always try to use something that would be more straightforward than spending so much time in just finding the zeros. So the only number that works out of this entire list is hopefully going to be 2/3. So what will my numbers be for my synthetic division from our polynomial here?
3,
-2,
-2,
3, -2, 12, and -8. Very good. Okay, so bring down the 3 as it is. And 2/3 times 3. 2. Very good. -2 plus 2, of course, will give us 0. 0 times 2/3 is also 0. Now, when I add 0 plus 12, I get 12. 12 times 2/3. 8 goes into 12. 4 times 4 times 2 is 8. So this will be +8. -8 will end up giving us 0. So yeah, that guy worked. He is giving us a 0 remainder. which means that's one of our roots, right? So we're good to go. Now, this is kind of what I'm talking about. Once we find our zero remainder number, use the quotient to go and find the others. So what is this quotient coming out to be?
Isn't that 3x squared plus 12?
Yeah, so this was a third degree polynomial, so this is second degree, 3x squared, that's a 0, so that means just plus 12, you have no x term there. So again, second degree polynomial, 3x squared plus 12, how can we find our zeros here? What strategy would you use? You can start by factoring out a 3. Okay, so what will that give us?
X squared plus 4.
X squared plus 4. And then what can I do with the 3? You can just divide both sides by 3, which will actually help you get rid of it. Because these guys cancel out, leaving us with x squared plus 4, and then of course 0 divided by 3 is 0. Now what can we do to get the x by itself? Subtract 4. Now what?
Square root.
Square root. Very nice. Square root both sides. And remember, anytime you bring a square root, you should have one positive and one negative root. These guys cancel out, giving us just the x by itself.
Plus or minus 2i.
Yeah, because remember, whenever you have a negative inside your radical, we think of -1, square root of -1 being our imaginary number I, right? So this negative part will come outside as I. Square root of 4 is going to be 2. So you're actually going to get plus or minus 2. So our roots for this polynomial is going to include the 2/3 that we got from the rational zeros. These guys are definitely not in order, so we've got 2/3 from that, and then I've got a -2i and a +2i from when we simplified the quotient, right? So third degree polynomial, and we did expect to see at most 3 roots, and in this case we did get 3 separate roots. So rational zero theorem is one of the theorems that we look at, which gives us the possibility of what our rational roots can be. But then, like I said, there's going to be other theorems which will help us narrow down the field a little bit, and that's what we will be looking at in the next section. But do you have any questions here? Yeah, that's the last one for number 7. Okay. So let's go to section 3.3.